The last example is taken not from the photosynthesis or not from the darkening of the blackening of the photographic planes, but from another type, namely from the electrophysiology, very nice experiments carried out with rod cells in the eye. Optical fibers will deliver the light to the rod cells. Suction fiber, you can carry out this type of experiments, and the illumination will be transmitted through the optical fiber. I do not want to go into details, but here you can see also the normalized amplitude, which can be evoked in the rod cells with different types of illumination, which can be coherent or pseudothermal. And here you can see that the deviation, considering the mean number of photons, a similar type of drawing figure constructed in the middle part of the lecture, but these are truly calculated examples. Here are the experiments with the experimental bars. Of course, the error bar is pretty large because these are real experiments in electrophysiology, but the distinction between the coherent and pseudothermal sources are quite obvious. So it is quite not arbitrary whether the rod cells in the eye are illuminated by a thermal light source or by a laser light source, more precisely whether with Bose-Einstein statistics or Poisson statistics. And this is the take-home message. I do not want to go into details. I just tell you that these usual classical characteristics of the light source, directionally, monochromaticity, high power, coherence, these are pretty vaguely used in discrimination between the different light sources. Among the different light sources, these are not absolutely unique to lasers. I would stress that the photostatistics can be more characteristics to laser light, namely the Poisson and Bose-Einstein statistics can be distinguished. We constructed also a light source where this transition between the different Bose-Einstein or Poisson statistics can be made as extricated of statistics, and this type of different photostatistics on the light source can be used for different parts of the biophysics. I mentioned here only the photosynthesis and maybe the electrophysiology. And I think this is the end of the story. Have a pleasant stay in Szeged. Thank you very much. Questions? If we have time.
Thank you for your talk.
Thank you.
Photon bunching, can we use it for example, for neuron or neuron or proton bunching on the other side without altering the basic mechanism? For example, using the previous scattering or coherence, can we target a particular neuron or proton?
Neurons.
Basically, I'm more interested in neurons.
Yes, practically this is the experiment with electrophysiology which I showed you. So then this can be also considered as excitation of neurons in the rod cells. It's practically the same.
But without altering the basic structure of the neuron, it's more for identification. For example, if inflammatory and non-inflammatory case, in case of medical inflammatory neurons, I want to just try the scattering because the wavelength in which it is activated or it is going to target, there's going to be very small, minute changes in the wavelengths between the two. So maybe with an external source.
I don't see the point. How is it connected to the wavelengths? So then it is practically.
No, I mean, for example, a particular neuron is you target with a particular wavelength. So using this coherence or scattering, can we just so that I can
With variable type of coherence.
Yes.
Yes. Theoretically you can. The major disadvantage is that this is scatter field. And this is not a conventional light source in that way. So the intensity of this light source is not extremely large due to the scattering property. So of course the laser light which will illuminate this ground glass object is very large, but the scatter field loses a lot of energy. And of course, with the changing of the speed of the rotating disk, it can be changed, the time of coherence. But nowadays, the intensity is pretty low, and I doubt that different sorts of neurons can be excited with this light source. Maybe, I don't know. I do not see quite clearly your problem, I have to admit. But I guess that you have concerns about the pseudo-thermal light source. It's a good construction, mainly for physicists that did this type of light source, but I do not know too much medical applications, and it can be done. Who knows? Additional questions? You? No? Sorry. Okay. I'm always telling that in this case my eyes move, the detector is sensitive for moving. So the students are frozen in that period of the lecture, not to show up any movement, because I will recognize it as a hand up and then posing questions to me. So you are not so brave to pose questions.
No, I was wondering, it's not clear for me how light emitted from the sun, for example, by the sun, can be coherent. It's not clear for me.
Because it is very far away. That is
okay,
why.
so you use, okay, you consider just a speckle of the light, not the whole light that you collect.
Everything is, which comes to the earth is very far away. So basically the take-home messages from this lecture that any thermal light source can be made highly coherent if you make spatial and time hindrance. So spatial, this means that practically you see just a spot of depth,
Yes, so you
or put it very, very far away. Then the coherence, time, and the length can be made so short or large as you wish. So this is why the laser light, usually the laser light shows much, much higher degree of coherence than light sources. It cannot be compared. For example, if you make a light source from xenon lamp, which is usually used in the optical spectral labs, practically the time of coherence is smaller than the lifetime of the spontaneous emission. This is surely the case. If the lifetime of the spontaneous emission, let's suppose 1 nanosecond, then the time of coherence should be much, much larger than 1 nanosecond. Compared to, for example, a well-balanced helium gas laser, where the power supply is made with great care, the time of coherence or the length of coherence can be kilometer and kilometer long. So practically the sine wave will be infinitely large, not infinitely, surely not. Compared to the fluorescence or thermal light source, where it has, for example, 30 centimeter, 1 nanosecond oscillation, and then nothing. Change, fade, and comes out something else. This, of course, the time of coherence or the length of coherence will be limited to this spontaneous emission process. But if this light source is taken away very, very far away, or you take a very small spot of that, then the degree of coherence can be increased tremendously. This is the best way for the sun.
But the intensity of the light that you use
This is
is
smaller.
not enough.
Yeah, that's another point.
Okay.
That's another point. In the case of the
It's
sun,
not usable.
yes, of course, but not always you need a large intensity. So that's not always is the tendency to get the highest everything, energy, power, brightness, everything. It's is not always the tendency, not always the aim of the scientists.
Anyway, I think we can continue this at the coffee break. Okay?
Okay, so again, thank you very much.
So please join us.